In this video, we're going to cover section 2.5, another section on applications, this time of exponential decay. So our objectives here are to find a function that satisfies the equation dp over dt equals negative k times p. Only difference from the last section when we were talking about the function where that was positive. Convert between decay rate and half-life, and then solve applied problems involving exponential decay. All right, so our definition says the equation dp over dt, derivative of p with respect to t equals negative k times p, where k is positive. So the negative sign will guarantee that it's negative. Shows p to be decreasing as a function of time. And the solution, just like in the last section, the initial value p naught or p sub 0, e to the power, this time negative k times t, since negative k is the coefficient in the differential equation model. So this shows to be decreasing exponentially. If you were to graph a function of this form, it would be moving downward. This is what we consider exponential decay. And again, the amount initially present at time 0 is this p naught value, the coefficient of the e to the negative kt. All right, so our exponential growth model from section 2.4, the graph looks like this. Whereas the model we're talking about in this section for exponential decay, which would have this equation, goes the other direction, right? They both hit the y-axis, however, at the p naught. Just one starts large and gets smaller, the other one starts small and gets larger. All right, so first theorem 10 here gives us the relationship between what we call the decay rate, which is the k in that model, and what we call the half-life. They're going to represent half-life by the capital T variable. So they are related in this way. Decay rate times half-life equals the natural log of 2, which is approximately 0.693147. You could rearrange this equation to have it solved for either k or t. If you would divide both sides by t, you would get k equals natural log of 2 over t, or again, that's the decimal value for natural log of 2. Or if you wanted to solve it for capital T for half-life, you could divide by the k. So half-life equals natural log of 2 divided by decay rate k. So we'll be doing some problems where we'll be given one and finding the other. So using this model in general or either of these two specific forms. All right, example 1, plutonium-239 is a common product of a functioning nuclear reactor. Can be deadly to people who are exposed to it. Its decay rate is about 0.0028% per year. What is its half-life? Okay, so we're given the decay rate, we're calculating half-life. All right, so our relationship here that we just talked about on the last page is if we're looking for half-life, that was the capital T denoted in the last formula, so half-life equals the natural log of 2 divided by decay rate. So the natural log of 2, 0.0028% sign means divide by 100. So notice here they've got 2 extra zeros in front of that decimal because to change this percentage to a decimal, you divide by 100, which moves the decimal point 2 places left. So in decimal form, that's 0.000028, which is then about 24,755 years. Which means the term half-life means the time that it takes for the initial value to be cut in half. This is a very slow decay rate, meaning that it's going to take a very, very long time for it to decrease to half the initial value. All right, so let's try another example. The decay rate of cesium-137 is 2.3% per year. What is its half-life? And then our part B, the half-life of barium is barium-140 is 13 days. What is the decay rate? So one we're calculating half-life, the other decay rate. All right, so half-life, natural log of 2 divided by decay rate. So natural log of 2 divided by, again, 2.3% would mean 0.023. Move the decimal point 2 places left, so 1, 2 puts 1 0 in front. And then on your calculator, that simplifies to 30.1 years. All right, if I'm calculating decay rate, our formula becomes K, decay rate equals natural log of 2 divided by half-life. So natural log of 2 divided by half-life, so divided by 13, gives me 0.053, which then I could write, if you wanted to, as 5.3%. Okay, and this is, notice, per day, because this unit for half-life was given in days. All right, our second example. The radioactive element carbon-14 has a half-life of 5,730 years. The percentage of carbon-14 present in the remains of plants and animals can be used to determine age. Archaeologists found that the linen wrapping from one of the Dead Sea Scrolls had lost 22.3% of its carbon-14. How old was the linen wrapping? All right, so first we're going to define our decay rate. Okay, so we were given half-life. So decay rate equals natural log of 2 divided by t, which was half-life. So natural log of 2 divided by our half-life gives us our decay rate to be 0.000120097. Then we're going to substitute that information into our model for decay. The function n equals the initial value n sub 0, or n naught, times e to the negative kt. So that 0.777 times n naught equals n naught e to the power. This was our decay rate. Hold on one second here. That's where that came from, right here. And the other number, notice it said here in the original problem that it had lost 22.3% of its carbon-14, meaning that it has 77.7% left. That's how much still remains. So notice here, if we go back to that slide where they just put that number in, that's where this number came from, 0.777 times n naught. So in other words, if 22.3% has been lost or has decayed, it means that there's 77.7%, so that's the decimal form of 77.7% of the initial value. So 77.7% of initial value equals the initial value E and then the negative KT power. They didn't really explain that on here, but you have to know where this number comes from. All right, so notice you can just divide both sides by n naught and they cancel. From here, we're trying to solve for t, and that's in an exponent, so we're going to take the natural log of both sides. So this side is still the natural log of 0.777. Over here by log properties, notice the base of natural log is e, and this is e, so this just simplifies to the exponent. And then you can divide both sides by this decimal in front of t. So on your calculator, when you calculate this, you get 2086, about. That would be, look like it's rounded off to that number. So the linen wrapping from the Dead Sea Scrolls is about 2086 years old. All right, and another example here. How old is a skeleton found at an archaeologist site if tests show it has lost 60% of its carbon-14? All right, so they're referencing the carbon-14 again, so we know its half-life, so we're going to need to use that to find our decay rate. And again, if it's lost 60%, that means 40% remains. So that's going to be needed when we go to solve for how old it is, okay? All right, so the decay rate, we know decay rate equals natural log of 2 divided by half-life, and for carbon-14, the half-life is 5,730. So natural log of 2 divided by 5,730 is 0.000120097, or 0.012097% per year. Right, to convert back to percent, you multiply by 100 and move decimal 2 places to the right. Then use this information from the problem and the K into our decay model. So remember, if it says that 60% has decayed, there's 40% of the initial value left. So that's the end. 40% of initial value equals initial value e to the negative kt. And this is what we had found to be k. So divide by the n naught on both sides, cancels it out. Take the natural log on both sides. The right side will simplify to just the exponent because it's a base e, and the log also has a base e, so our log properties let us simplify to just the power. And then we can divide by the coefficient, that decimal coefficient in front of t. And then on your calculator, that should equal or approximately equal 7,575. So that skeleton would be approximately 7,575 years old. All right, third example. Following the birth of their granddaughter, two grandparents want to make an initial investment of a certain amount of money, P naught, that will grow to about $10,000 by the child's 20th birthday. Interest is compounded continuously at 4%. What should the initial investment be? How much should they put away now if that's their goal? So we're going to use this equation. This is growth. P equals P naught e to the kt. So we're looking for present value, right? We're looking for the P naught. That's what we don't know. All right, so 10,000 is what they want to end up with. So that's our P. Initial value E 0.04, because it was 4%. And they want to have this amount of money at their 20th birthday, right? So T is 20 in 20 years. So 0.04 times 20 is 0.8. To solve for the P naught, we would divide both sides by e to the 0.8. And notice here that you could bring this up to the numerator and that would change your sign of your exponent. So basically they're kind of showing with this example, if you were to take that growth equation and solve for the P naught, which would be present value, you get a decay equation, right? And the amount they're going to invest, the amount that they want to end up with this time, e to the power negative 0.8. All right, they calculate that and they get $4,493.29. Means if they put that amount of money into an account today, by the time the child is 20 years old, they will have $10,000. All right, so let's repeat that example if the interest rate would be 6%. All right, so again, start with that growth equation for compound interest, knowing that the value we want to have at the end, which is this P, is 10,000. This time we're going to use a 6% interest rate and again 20 years. So 0.06 times 20 is the 1.2. Dividing both sides by e to the 1.2 gives me $3,011.94. So they must deposit $3,011.94, which will grow to $10,000 by the child's 20th birthday if the growth rate is 6% versus 4%. So that plays a role, right? They don't need as much money now because it's growing at a faster rate. All right, so present value. So remember when they rearranged that equation to solve for the P naught, they had P, which would be how much you want to have at the end, e to the negative kt. So present value of an amount, P, due t years later at an interest rate of k compounded continuously is given by this. So if you were to solve that equation for P naught without plugging numbers in for the P and the K, it would end up being this equation. So that function satisfies, that function, you could just use this model instead of starting with the compound interest continuous growth model and get the same answer. All right, our last law here that will help us do the last problem in the homework is called Newton's law of cooling. The temperature T of a cooling object drops at a rate that is proportional to the difference, T minus C, where C is the constant temperature of the surrounding medium. So in other words, the derivative of temperature with respect to time is negative K times the difference between the temperature at whatever time and the initial temperature. The function that satisfies the above equation is this. The temperature, or temperature as a function of T, is A e to the negative KT plus C. Remember, C is the temperature of the medium. All right, so we're going to use that model to do this example. A body is found slumped over a desk in a study. A coroner arrives at noon, immediately takes the temperature of the body and finds it to be 94.6 degrees. She waits 1 hour, takes the temperature again, and finds it to be 93.4 degrees. She also notes that the temperature of the room is 70 degrees. When was the murder committed? When did they die? All right, so the temperature of the room being 70 degrees tells us that's the C value in our formula. The initial temperature, 94.6, and then the temperature after 1 hour, 93.4. So all of those things are going to be used here. All right, so T is the time elapsed, with T being 0 representing noon when she first took the temperature. All right, so our model that they gave us on the slide, they gave us the formula for Newton's law of cooling. What the equation we use is that the temperature of the body initially, 94.6, equals A, we don't know that, e to the negative k, T being 0 here, meaning at time 0, right? At time 0, it was 94.6 degrees. We're just plugging those in, and then our temperature of the room was 70. That's the C value. All right, e to the power of 0 is 1, right? This exponent would be 0. E to the 0 is 1, so this is just A plus 70. So they just subtracted 70 from both sides. So 94.6 minus 70 is 24.6. E to the 0 is 1, so this right side becomes just A. So that's our A value. So our function becomes T equals, we calculated A right here, 24.6 e to the negative KT plus 70. Okay, so the first step is to use that model to find A using the initial temperature. All right, to find the number of hours since the murder was committed, we have to find our K value. So we were also told that after 1 hour, the temperature was 93.4 degrees. So in that model we just found, so 93.4 is the temperature. We just found that 24.6 was our A value, e to the negative KT. This time this temperature corresponds to a T value of 1 in the given problem, plus the 70. So if we subtract 70 from both sides again, we get this. And if we need to solve that for K, next step we're going to have to divide by this coefficient. So divide by 24.6. Oops. First, that leaves 23.4 divided by 24.6 equals e to the negative k. Take the natural log of both sides. Notice they've moved the negative over. So if I just took natural log of this side, they would not have the negative. They'd have natural log of that. If they take the natural log of the right side, natural log of e to the negative k is negative k, right? Because of the base of the log being e. So when I take the natural log of this side, I get negative k. They just moved it over already to the other side. So on your calculator, that gives you about 0.05 for your k value. So that would give us your model to be your A value, e to the, we just found k to be 0.05, so negative KT plus your temperature of the room, 70. All right, so determine the time of death, assuming the individual had a normal body temperature of 98.6 when they died. Meaning you're going to plug 98.6 into that model and solve for T. All right, so this is calculated by subtracting 70 and then dividing by 24.6. Now we take the natural log of both sides. They left the negative over here this time. Then calculate, so doing natural log of 28.6 divided by 24.6 and hitting equals, then dividing by negative 0.05 should give you about negative 3.01. Meaning, since time 0 at noon, the time of death was about 3 hours earlier, right? Time being 3 hours before 0, right? Meaning that negative sign, right? So about 9 a.m. All right, so the summary for this section, decay rate and half-life are related by the equation decay rate times half-life equals natural log of 2, which could be solved for either K or T, depending on what you need. Present value, P naught, of an amount P due T years later at an interest rate K compounded continuously is given by this equation. So the present value equals the future value, e to the negative kt. And then Newton's law of cooling model for the differential equation is this. However, this is the function form that we utilize to solve problems that involve Newton's law of cooling. Temperature equals A e to the negative kt plus C, where C is the temperature of the room, and then you would calculate the value of A and the value of K based on the given information in the problem. All right, so that is the end of section 2.5.